So now let's talk about stability. And stability in your structure is very easy to achieve if there are no loads, nothing affects it. You can just sit here forever like this, right? But if you got the wind blowing, you got forces on it, you got drilling, now you start having the issue of not only structural stability in terms of static loads, quasi-static loads, not causing, boom, for example, the shear center problem we showed earlier by pushing off axis on a beam, but dynamic loads of exciting natural frequencies. So the classic example is the Galloping Gertie Bridge over the Tacoma Narrows in Washington. Beautiful bridge, wonderful, marvelous, architecturally marvelous, static, oh, such a good bridge. And then the wind came through and then whoosh, whoosh, bad. So how do you design for dynamic stability? To the very first order, we're going to be aware of the stiffness of the structure, which you can estimate first order calculations and or finite element analysis, and of the mass of the system. So to our very first order natural frequency, going like the square root of k over m, for just very, very simple first mode guesstimates of, am I in the range of I'm going to have a problem or not? Well, it's going to depend upon what the excitation frequency is. And if the excitation frequency is either much less or much greater than the structural natural frequency, at least you have a hope of it being okay. At the layout stage, this is all you can do. As you get into the detailed design phase, then finite element modeling can be very, very valuable in starting to predict much more accurately what the vibration mode shapes are and the natural frequencies are. And as long as you're designing your structure with the intent of using the neutral axis theorem to keep most of the mass away from the neutral axis, like for example, it's an I-beam, and you have provisions for how you can add more mass far away from the neutral axes of the members or add in diagonal stiffening elements without obstructing the motions that are intended, you at least have a strategy or countermeasures for the risk of natural frequency too low. Remember, when you design a structure, the loads that fields that you're designing for are not necessarily going to be the loads that are going to fail the structure. It's going to be the unexpected loads. Very, very important to always try to think ahead to what could go wrong. The next type of stability issue to think about are obstacles. As the structure is moving, what kind of obstacles will it encounter? For example, this is the design of a vehicle that's supposed to go over a bump. How does that affect the structure and the layout of the machine? For example, if this is a four-wheel vehicle and one tire has to go over a big rock, if the chassis was just a plate with four wheels on the corner, I would be coming along as I'm driving along into a condition where one wheel goes high, and the machine, it would now be like a four-legged stool with one short, and the structure would rock, and it would be unstable. I'm sure everybody's sat in a four-legged chair, had been at a table at a restaurant where one leg is short and the thing rocks. In a vehicle, that could cause it to go unstable. Old-style tractors, and even new tractors, will do this. Back part of the structure, front part of the structure, and a pivot between the front and the back. So the front and the back can pivot with respect to each other. The pivot is then designed to be strong and bending, and now I can accommodate varying ground, and this pivot between the front and the back of the structure makes the vehicle emulate as if it was a three-wheeled vehicle, yet have the stability of a four-wheeled vehicle. Okay? So stability for loads, dynamic loads, and obstacles design in compliance where needed, design in the ability to increase the stiffness as required. Stability also, when your structure is moving, will it all of a sudden come to a point where a little more load sends it unstable? Is there a condition on this drill press where if I have the table and it moves off to the side and I have a heavy load that I'm drilling a hole in, will it cause the whole thing to tip? There's a couple of really scary industrial applications of this, or I'm not sure it's called an application, but a de-application, which was vending machines. And some really brilliant people discovered that if you shake them, you can rattle the cans out until they would fall and you get a free soda. Now, unfortunately, in the context of shaking the machine, the following was discovered. Don't try this at home, kids. See, I'm applying just a little bit of force. I'm not applying any more force, but I'm now just exciting it. Watch what happens when it crashes over and hurts me. Don't. Right about there. Okay, so this is about the angle at which it'll tilt and get hurt. So you'll see soda machines now often with stickers. Do not rock to attempt to get free soda. That didn't work so well. So the sticker is bigger. And I don't know the exact wording, but basically it says, machine design, no matter how hard you rock this puppy, you ain't getting a free soda. Arr. That pretty much stopped the problem. And people discovered they couldn't do that. What is your liability as a designer, or indeed a manufacturer, if you design a machine that if people are a little aggressive with using it, if it tips over and hurts them? Dumpsters were another type of structure that had this stability issue. If the dumpster was empty and kids like to climb on the dumpster and on this front end, would the thing tip over and crush them? So even though you may not intend to have your structure used in a way that it could have an instability issue, you have to assume that it will be misused. How would you attack it? And one of the really good ways to do this kind of evaluation on your machine, go find some kids, maybe some teenagers somewhere, in the summertime, they're bored, they've got nothing else to do. Build a plywood mock-up, something that's safe. Say, okay guys, you're bored, what would you do with this thing? How could you hurt it? So go ahead and don't just ask a bunch of professional people with ties who look very serious all the time. Ask some folks who are bored, hey, what would you do with this? You watch, they'll discover things that you as a brilliant, marvelous, extra special designer, wow, I never realized you could woo with that. Woo. Now, let's get into some of the detailed parts of the design. And by detailed parts of the design, we start to look at how do you go from the layout to real fine detail, like stress concentrations, which may seem, whoa, wait a second, it's getting a lot more detail when you just went from layout to this level of detail. What's happening? The key is thinking about boundary conditions on your structure, because when you start looking at these levels of detail, it may actually cause a fairly large change in when you go from the broad concept detail layout to the detail layout. So for example, look at structural connections issues. If you have two beams laying on each other, the force applied to them, or in other words, laying on each other but without a real stiff connection, just a simply supported type connection, what is the vertical stiffness of this compared to if these two members were perfectly connected? It turns out that this system is significantly stiffer than this system. And the reasoning is you're pushing here, this beam is under bending, and as it bends and it deflects downward, it has a slope to it. So as this beam here, as you push on it, bends and deflects down, its neighbor over here, in order to accommodate this slope, as this one bends down, it also has to twist, so it acts like a torsion spring to keep this one up. The lesson here, on this level of detail, you start thinking about manufacturing and do you use discrete elements or should elements be formed and then attached, is that it may seem simpler sometimes to use two simple parts and then I'll connect them as opposed to one part that I had to do a bend. The stiffness and strength of joints becomes an issue to be wary of. The stiffness and strength of joints, in particular the strength issue, when you start having stress concentrations wherever you have a physical joint between things and you have a discontinuity. When I form something, I can often put a nice, big, gentle curve in it, which can help to reduce stress concentrations. Remember, you're designing your machine typically not just to last for a day or a week, but for years. Coming back to the stiffness question on detail, you can look at something like some of this modular aluminum structure, which is really, really, really handy, and it goes by a bunch of different trade names. And it's really wonderful and handy because you see, notice there are these dovetail structures in the sides that allow you to bolt stuff to it, and you can, like a modular kit, very easily build up very complex machine frames out of this stuff. Very, very handy. On the other hand, if you've ever worked with this stuff before, you'll note that torsionally it's not so stiff. You have a big structure and just a post and a load on it. It really woo-wah, woo-wah. And why? And the reasoning is, if you look at it, it's an open structure everywhere. In torsion, when a structure is open, it's an order of magnitude less stiff in twist than if that same structure is closed. Okay? An order of magnitude less stiff. So when I look at this type of modular structure, and I want to build a machine from this stuff, how would I do it? How would I make this thing torsionally stiff? When I have to buy it this way, what do I do? Well, one of the, quote, answers is buy a slightly bigger section that may have a bigger part that is a closed section, but now you start getting it really big and you start paying a lot of money. To modify this would take away the ability, for example, to just attach anything anywhere along it. What would I do? What would I do? How would I think about a closed section? Why, when I'm designing with structural steel, if I use an I-beam, is it really stiff and bending, yet if the structure has any torsion, all this thing flexes all over the place? When do I use an I-beam versus a box section? Now, the torsional stiffness of these open sections can be very easily determined, even some more complex ones, by these simple formulas or the more complex exact forms for some common shapes are given. But any of these open sections, while they're very useful in bending, remember they're basically useless in torsion. You don't pay that much more for a closed section, but these would be very, very good for bending and torsion, yet not as efficient necessarily with respect to the weight of the structure because I've got a lot of mass that's close to the neutral axis and is not as efficient structurally as this mass away from the neutral axis for taking bending. So again, it's balance. What is the function required? Which design do I need to use? And here are the analysis tools to get you there. So while I've been burbling away, you've probably been thinking, yeah, I've got the answer. So I somehow need to close the sides of this. If I could somehow close the sides, I would now have a closed path for the torsional structural loop. Indeed, I would also be adding mass far away from the neutral axis for bending resistance. And there's a couple ways you could envision doing that. You can envision building your entire machine out of this stuff and then taking thin sheets in the parts that are exposed and attaching them. And how would I attach them? I don't want to spend all the money on bolts and nuts and putting it all together. Remember there's this stuff called tape. And this is not double-sided tape, but you can buy double-sided tape, which means that you could very easily put double-sided tape on your structure and then attach, as a last operation, plates. So you would close the section. The tape would give you immense stiffness now with the plate you've added. Plus, the tape is a little bit soft and goopy. Not too much, still get very high stiffness. Yet the softness would also provide damping. So you could get a fair amount of damping from your machine by doing this addition of a plate with double-sided tape to these open modular sections. So that's a really good structural trick to remember if you're designing machines whose frames are built up with this modular aluminum. But be careful, because if you overload the tape, the joint will fall off. So you have to calculate the shear stress that joint will see, and also be very careful of the temperature that your machine does. Now, we've been talking about stiffness of the machine as if every machine should be infinitely rigid and stiff. There are a lot of machines that you want to have compliance built in for energy storage, for taking shock loads. You want to design your machine to have a springiness to it because, face it, in a car, if there was no suspension, it's really rough to drive. And if you've ever driven some construction machinery like a bulldozer, and with a bad seat, or a tractor which has no spring, an old style tractor has no spring in the seat, you come back, my back is sore at the end of the day. So being able to put in the compliance you want to lower the forces that are seen by the structure or the user when they're applied by allowing some give. And remember, we started this, we said read the oak tree and the reeds in Aesop's fable. A very, very critical fable to read and really take to heart. Okay? That's the last hint I'll give for that. Now, let's explore some of the things you can do with shapes for achieving either stiffness or compliance. And remember, stiffness is 1 over compliance. In terms of stiffness is given as, for example, newtons per meter, and compliance is given as meters per newton. Here is some plastic, a sheet, it's just a normal plexiglass, very, very compliant. Here is the same type of, and this is a much thinner sheet with some shapes in it. This is stiff this way, much stiffer. It's still relatively soft this way. Why is it soft this way? And notice these are like chevrons in it. It's pretty soft this way, yet this way, it's pretty stiff. What's happening? And this looks like an egg crate. It's compliant in torsion. It's stiff that way, and it's stiff that way. How does this plate made, what's the shape of these features that makes it stiff and bending in 2 axes? And why is it still torsionally compliant? Why is that? Is there a way I can take one sheet and put features in it such that it's torsionally compliant, or excuse me, torsionally fairly stiff, and bending stiff, and bending stiff? What's the magic of the shapes that allow that to happen? All made with a thin sheet that has been vacuum formed. And then, of course, so that's with one part. What happens when we take a sheet, and something in between to make kind of a modified cardboard? And you know, cardboard normally is stiff in one axis, but the other axis along the corrugations is very compliant. Why do they do it that way versus not this way? So there's a lot of magic to what you can do with structures by working with the concept of the neutral axis and closed versus open sections with respect to torsion. All of this is based on, one, your physical understanding because you felt things, you observed the sections, being able to do first order analysis very, very quickly, because I can do first guesstimate of the stiffness of a structure far faster than you could ever design it in a solid model, run finite element analysis in it. By the time it takes you to do that, I may have gone through 2 or 3 or 4 iterations by using just basic first order analysis, closed form solutions in a quickie spreadsheet. So you want to become adept at doing that. It's analogous to snowboarding or skateboarding. You can read the manual now. Okay, now if I want to turn to the right, I'm going to go, assuming I'm riding normal footed, toe it, bam! The tree hits you. So you ain't got time to think about this stuff in design, because while you're thinking carefully through it and your competition has already come out with a design and beat you. Okay? Got to be fast in design, and you got to be right. There are a lot of different analytical methods, from simple closed form equations you get out of a book to, for your particular structure and its loading conditions, I can't find this model in the book anywhere. So get good at deriving the solutions from your basic first principles. Energy methods are one of my favorite ways of doing this, particularly for more complex structures. And remember, when you develop the closed form solution for your particular structure, so you get the equation that says how it performs, you can put that into a spreadsheet or MATLAB code or whatever you'd like to use to play what-if analysis. And once you have that closed form solution, you can bang off 10 different parameters and investigate many different designs whilst the other person is still logging on and attempting to figure out how to drive the software for their finite element code, for example. Even the ones who are very good at it can't respond in general as fast as you can when you have the closed form estimate. With the closed form estimate, to get you in the neighborhood, essentially tighten up the layout of the structure, enabling you to create what is a much more, quote, final shape in the solid model. Then you go to the finite element analysis. So here we have, for example, energy methods analysis. We're obviously not going to go through in the lecture on tape all the equations. But what it lets you do is derive the stiffness of this curved beam. And you can say, well, I can look that up in a handbook. You derive the stiffness of the curved beam for any arc and with a lot of different types of loads. And some handbooks may or may not give you the actual answer. But even if you go to the handbook and get the actual answer, that's good. You'll have it in the concept of, in the context of, for a curved beam with this arc, how it deforms the stress and deflections as a function of the loads, which would allow you to play the what-if analysis of how big of an arc do I need, for example, in order to get the stiffness of a spring. You also have to be careful of how your theory goes in terms of when the beams get real short and stubby like gear teeth. We'll look at these gear teeth over here. What's the stiffness of the gear tooth? It shows so short and stubby that you can't just apply classic Euler beam theory to it. The shear of the teeth becomes one of the dominant displacement modes. Well, it turns out using energy methods, you can calculate the deflection due to the bending and the shear as a function of the varying cross-section of the tooth. Very straightforward to do. And now you have your closed-form solution for the stiffness of that gear tooth, and would allow you stiffness of your rotational mechanism governed by those gears or controlled by those gears. It's stiff enough. It would allow you to very quickly play what if with the mod of the gear. Remember, the mod would be, in terms of the mod in millimeters, would be telling me how many gear teeth I have around this entire circle. Okay? So the mod of the gear, when the mod gets bigger, I have a much bigger tooth and much stiffer, although then I start having higher gear tooth separation forces. I start having not as fine resolution of motion of control, but it's much stiffer. So there's always a trade-off. So if I can write all that into one spreadsheet, so I can very rapidly go through the stiffness of the gear, the strength of the gear, I can play what if with different mods very, very quickly. In the end, check with your finite element analysis just to be sure. But remember, the name of the game is to be able to move quickly through your design. Another very important thing to remember when you're doing finite element analysis, when you get to it, is the following. A lot of machines are designed using solids in the solid modeler, and then they use the auto-meshing programs to create the mesh of finite elements upon which the analysis is performed. If you were to take just a beam from a solid model, there's a beam in my machine. Let's say the machine is supported by other parts. It's being loaded by some loads on a carriage. And I'm looking at this beam and I want to know the deflection of the beam and the strength of the beam, and maybe I'm going to do that because this is some weird shape like we just drew earlier, this guy with the plates on it. And I did my first order analysis assuming that it's just the top and bottom plates that governs the stiffness. But you know, I want to check it, particularly for things like torsional loading. Well, okay, I'm just going to take this beam and I'm going to load it, simply support it, load it, see what the stiffness is. You've got to be really careful, because if you just say, well, it's supported at the end, so I check this surface and this surface as constraints, and then poof, do the finite element loading, I will get a shape that looks like this. In other words, if you check a surface to be constrained on a solid, it doesn't allow any rotation. Even though you know when you're putting your beam in your machine, hey, it's not being held infinitely rigid. So this is wrong. The beam is not going to bend like this. It's okay when you're designing your layout and you know you're going to be doing finite element analysis. Remember, you want to visualize the structure and how it deforms, what it does. So I can add this little tab here. But notice the proportions. This is 1 unit across. This is 10 units tall. So St. Venez say that if I anchor this here, this will not be able to affect this structure here with respect to bending. It will only provide vertical support. And now you see that the structure is, I'm getting the actual shape. This is also true for bolted joints. And we will be talking about this a lot more in the next topic, topic 9 on joints. There's a way you can model bolted joints very, very effectively in your solid model such that when you do the meshing for finite elements, you get a very accurate prediction of the stiffness of a bolted joint. So there are some tricks you can play using when you're doing finite element analysis where you're adding in compliance to free up the anchoring stiffness so it behaves the way you see, that's the way it actually is going to behave in the machine, while maintaining the, for example, linear stiffness in the directions where you know it's going to be stiff. Similar modes of thinking for torsion. So do not be afraid in your solid model layout of your structure to add in compliance cuts to enable the finite elements to be accurate, or compliance structures to enable it to be, the results to be accurate. Now, most machines are not designed as just blocks with some stuff removed. Remember, most machines are constructed of beams and plates. Closing the loop through the plate is very important, as we showed with these different structures here. These started out as plates, and with these structures we added features to them to stiffen them up, to make them thicker by giving us an effective deeper depth. This is the section from a Berge wind turbine blade. Notice how, and this is a pultruded fiberglass, how this aerodynamic section, this airfoil, was actually pulled out or pultruded as one piece, very, very, very torsionally stiff, bending stiff, but simple plate sections. So remember the power of neutral axis theorem in using extrusions and extrusion type processes to achieve very, very high stiffness and strength from what otherwise may be thought of as soft plates. In plates in particular, if you take just a flat plate, as we've seen, that can be, it's very, very soft. But watch what happens when I take a plate that's bent. So here's a plate that's just straight, and I push on it. What? Watch what happens when I push on it, it's bent. Now it's actually stiff, like a dome or an arch. Looking at air conditioning, heating, ventilating, and air conditioning ducts. Why? I mean, here's a ductwork, piece of ductwork, and here are these sections that are put together to form your air duct. Why do these sections look often like they've got these crosses in them? And when you look more carefully, indeed these are creases. And what happened was a flat plate was taken and it was formed, bent, such that it's a mini pyramid. It's a pyramid of, so I do a cross section, I'll see it goes up and down. And it's ever so subtle. It may only be on the order of a centimeter or less over a range of 100 centimeters. But that's enough to make these plates stable so they're not a taut diaphragm, because a taut diaphragm will oscillate between the two modes, this mode shape and this mode shape, because it's neutrally stable. Remember, see, we're going back to that stability discussion. You often want to bias things in the direction, one direction or the other, of the particular mode shape that you're trying to quench or stop and leave it there. Now it's much, much more stable and stiff. So you can discover that doing your finite element analysis, looking at adding ribs or pre-displacing structures to get very much higher degree of stiffness.